Hi there. What I'm going to do in this video is I'm going to show you a couple of types of problems. One is connected to the ones that we looked at in the previous video. And then one is leading us into the next section, section 15.4, when we're going to look at what are called ice tables. So this is somewhat of an ice table right here. So let's begin with it. Let's take a look at it. The first one I'm going to bring up involves writing equilibrium constants for a reaction sequence. So now we're going to combine equations. This is something that chemists actually do sometimes when they're making calculations, and that is to combine chemical equations. Okay, it's a very famous type of problem called the Bourne-Haber process or the Bourne-Haber cycle, which is sometimes covered in the first semester of general chemistry, where you combine a bunch of equations to get one desired equation. And that's essentially what we're going to do here, just with a couple though. So it says here that we have the reduction of iron 3 oxide to iron using or during steel making can be summarized by the sequence of reactions. So the first reaction is 2C solid plus O2 gas in equilibrium with 2CO gas. So that's carbon plus oxygen to form carbon monoxide. And there's a K value for that. We'll call it K1. There's no number here, but there's the value. Okay. Then we have Fe2CO3, which is iron 3 oxide, combining with carbon monoxide to form iron and carbon dioxide with a K2 as well. The net reaction is, so they give us the net reaction there. We want to write an equation that gives the overall equilibrium constant in terms of K1 and K2. Okay. So let's take a look at putting together what's actually happening in this problem. Okay. Okay, so we have one reaction, which is 2C solid plus O2 gas, and that gives us 2CO gas. And then this is K1, okay? Now, I'm going to write down the second one right underneath it, Fe2O3 plus 3CO goes to 2Fe plus 3CO2, and this is K2. And then what we want to do is we want to figure out what the K is for this reaction. Okay. So in the end, this reaction produces so much heat that it essentially melts iron. So you end up with iron as your product right there, Fe. That's how we're going to make steel essentially. Okay. So let's take a look at that overall, or that third equation. So if you look at it, what you see is it has Fe2O3 as a reactant. So does this one. So there's something in common there. There's also, in this reaction here, there's carbon, and there's carbon here. Okay, that's fine. Then there's 4Fe here, there's Fe here. Same state of matter, by the way, they're liquid. And then you've got the CO2 over here, which is also in this equation. Okay, so I'm going to make a couple of observations about this. One is, it appears as though it might be possible for us to get this third equation here by combining these two equations in some way. And that's essentially the idea that we're looking at here, is that you combine equations to get a third equation, but it doesn't exactly work out. And the reason are essentially the numbers. See how you have 2 carbons here, but we have 6 over here? And you see how you have Fe2O3 here, but you have 2 of them here. So here's what I'm going to do. I'm going to do a little manipulation of these top 2 equations. I have 2 carbons here. I want to have 6 in my overall equation here. So I'm going to multiply that by 3. So I'll put this in brackets or in parentheses. And then we'll see if that works. Okay, we'll see if that helps. Now, remember what we said in the previous lecture. You can look back in that video if you need to. If you multiply an equation by some value, you raise the equilibrium constant to that same coefficient. So if I multiply that equation by 3, I take K1 and I raise it to the 3rd power. That's cubing it, right? K1 times K1 times K1, not 3 times K1. That's different. That's 3 times as much. Remember, we went through it in the previous lecture why that's the case, but we raise it to the exponent. Likewise, if we have a 2 Fe2O here, Fe2O3, why not just put a 2 here and see if that helps? So for that second equation, I'm going to multiply that by 2. And again, you would make that an exponent. You would square it. Okay. Now the question is, does that actually give us this third equation? Is it going to give it to us? Okay. Well, we have 6 carbons as a solid, as a reactant. That's what we have here. So that looks pretty good. We have 2 Fe2O3 as a solid as a reactant. That looks pretty good. By multiplying by 2, we now have 4 FeL here, right? Fe liquid, which is exactly what we want. And by multiplying by 2, we would have 6 carbon dioxide. So that looks pretty good too. So here's what I'm going to do. I'm going to take the K1 and K2, and I'm going to go ahead and rewrite them with those coefficients that look like they're going to work. Okay. So I'm multiplying the top one, K1, by 3. Okay. And then that's going to be K1 cubed, right? And then let's do the second one, 2 Fe2O3 solid plus 6 CO gas gives us 4 FeL plus 6 CO2 gas. And then that's going to be K2 squared. So if this is correct, then adding the 2 of them together should give us this overall equation down here. Okay, so let's see if it does. We can cancel the carbon monoxides. There's 6 of them on both sides, so that can be canceled. And it looks like we're getting pretty close there, right? Let me just make sure. Yeah. Oh, I'm sorry. I made a mistake here. There, in the overall equation, there were supposed to be 3 O2s. I'm sorry. That was in the problem, and I just forgot to copy it over. Okay, so it looks pretty good then. So it looks like we're going to have 6 carbon solid, 3 oxygen gas, 2 Fe2O3, and then that's going to give us 4 FeL plus 6 CO2G. L for liquid, G for gas. So it looks like that's good, worked out. Okay, now the question is then, what's the K equal to here? Okay, now let me show you something. Suppose I say A goes to B and then B goes to C. I'm going to put this in equilibrium. Okay, well, K would be, for this one, K1 we'll call it, is, you know, either pressure or concentration of B over concentration of A. And then for this one, the second one, K2 would be concentration of C over concentration of B. Okay. Now suppose I had this, A goes to C. I combine those two equations. If I just combine those two equations, the B's cancel and you have A goes to C. K would just be concentration of C over concentration of A. Well, it turns out that's the same as taking K1 times K2, multiplying them together. Concentration of B over concentration of A times concentration of C over concentration of B. These cancel and you get C over A. So it actually turns out to be okay. So here's what happens. If you combine equations, if you're adding equations, you multiply the K values. So here, this would be K1 cubed times K2 squared. Okay, that's how that works. So you just multiply the K's together. It just works out that well. What works out that way. Okay, so what that tells us then is that if we know the K value for one equation, we can multiply it by a coefficient and then figure out what K is now. We can do that for the second equation. And then if we're going to add the two equations, we just multiply the K's together. Okay. Now I just want to make sure as I look at this. Okay. Yep. Not a problem. Okay, good. Let's take a look at one more. That's the same one. I don't want to give you exactly the same problem. Okay. Let's try this one. Okay, writing the equilibrium constant for reaction sequence. The first two steps in the industrial synthesis of nitric acid produce nitrogen dioxide and ammonia. So 4NH3 plus 5O2 gives you 4NO plus 6H2O, and it has a K1. 2NO plus O2 yields 2NO2, there's your K2. The net reaction is, and then here's our net reaction, 4NH3 plus 7O2 gives us 4NO2 plus 6H2O. What's the K? Again, we want to write the expression for K in terms of K1 and K2. Okay, this one actually looks a little simpler because it looks like we don't really have to do much in terms of manipulating the individual equations. Okay, so let's take a look. This one's a little easier than the previous one, I think. So 4NH3 gas plus 5O2 gas, and that's going to go to 4NO gas plus 6H2O gas, and there's your K1. Okay, second equation, 2NO plus O2. This time I'll try to make sure I get everything written in there. 2NO2 gas. Okay, that's a G there. And this is K2. Okay, so they're saying the net equation. Well, when they're saying the net equation, I think that just means you're just adding them up. So you're not really having to do any manipulation other than just adding them. And we want to know what K is. Okay. Okay, hopefully you can see that well enough to scratchy writing. Okay, so we want to know what K is. So let's just check. We've got 4NH3 here and here. They're both on the same side and the same number of them. So it's not like we have to multiply by some number to change it into 4. There are 7 O2. So what happens? Well, there's 5. One more would give it 6, but not 7. So something is going on here. So let's keep that in mind. Maybe the O2, we need to do something. Then we have 4NO2. Okay, well, here's NO2, but there's only 2 of them. So there's your key. There's only 2 NO2, not 4. But the water looks okay, right? 6 water, 6 water. So it looks like this equation at the top, K1, is okay. We don't have to multiply that by anything because we've got the right number. To be honest with you, if you got the right number of really any of them, it's going to work out. If you got the right number of ammonia, if you have the right number of water, it's got to be right. Okay. But the second equation, there is a problem because there's only 2 NO2 and we want 4. So I'm going to double everything. And you know what that's going to do? That's actually going to fix the O2 because now, forgive me for leaving the states of matter out here, but I just want to show you how the numbers work out. We don't use the states of matter in our calculation here anyways, right? Now we're going to have 4 NO plus 2 O2 gives us 4 NO2, and then there's our K2, right? Now see how that works out? We now are going to have 7 O2. That's what we wanted. 4 NH3. 4 NO. Okay, I think I've got everything on the left side. Then we're going to have 4 NO plus 4 NO2 plus 6 H2O. Everything looks good except the NOs are going to cancel, right? And that's just going to leave us with 4 NH3. Now I'll go ahead and put the states of matter in. And we've got it. That's exactly the equation that we needed. We just wanted to add those two equations together. Okay, now let's go back. Let's remember the first one, we didn't really change anything. It's still K1, but K2, we multiplied by 2. So we have to square that. So now if you add those and you get the equation that we're looking for, you multiply them together. So K would just be equal to K1 times K2 squared. And there you go. There's your mathematical expression. Okay, pretty nice, right? In theory, you could do ones where you have to reverse equations too. Remember, if you do reverse an equation, you just take 1 over K, right? It's the reciprocal of the K value. So if you find that you have to reverse one, just take the reciprocal of K. If you then have to multiply by 2, square it. And then if you have to multiply by 3, cube it. You know, that's all you got to do. Okay, so that's a nice little, cute little problem to figure out K for a reaction that you may not know the actual value for. Now what I want to do is I want to show you, this is getting into sort of the details of how we deal with ice tables and all of that. So this is still in section 3. I'm not exactly sure why it's in this section. It seems like we could put it in another section in the next one, but that's okay. We'll deal with it now. And it's called the small X approximation to solve equilibrium problems. It's a cool problem, actually. A chemist is studying the following equilibrium, which has the given equilibrium constant at a certain temperature. So they're giving you this equation. It's a balanced equilibrium equation with the value of K. And then it says that the chemist, he fills a reaction vessel at this temperature with 11 atmospheres of nitrogen gas. So that's your N2. 7.5 atmospheres of hydrogen gas. That's your H2. Use this data to answer the questions in the table below. So normally we would go through ice tables first. So we'll kind of introduce this a little bit here. Can you predict the equilibrium pressure of ammonia using only the tools available to you with Alex? Yes or no? I've gone through many of these and it seems like the answer is always yes. So I don't want to tell you that it's definitely yes, but all the ones that I've looked at seem to be yes. If you said yes, then answer the equilibrium pressure of ammonia at the right. So you're just going to enter in what the equilibrium pressure of NH3 is and round it to 1 significant digit. Okay. All right. So this is actually a pretty famous equation. So I'm going to go ahead and write it down and then I'm going to explain how this all works. So we have nitrogen plus hydrogen forming ammonia. Make sure you get those coefficients correct. And then Kp I'm going to write it out just like we learned how to do it in the earlier sections. You take the product, oops, sorry, we're doing KP. So you take the pressure of ammonia and you square it, right? Products over reactants, pressure of nitrogen, pressure of hydrogen, cubed, right? And then they give us this value. And what I want to point out is the value is, in all these problems, is very small. This is a small X approximation to solve these problems, which works pretty well. Okay. I'm actually happy that they give you this problem because it actually shows you how to solve a pretty cool problem. Okay. So here's what they tell us. And I'm going to go ahead and introduce us to what's called the ICE table, initial change equilibrium, ICE. Initial are the pressures they give you at the beginning. These are going to be given 11 and 7.5. And then this is 0. If they don't tell you how much of that is put in, if they don't give you any indication of it, then it's 0. Okay. Now here's what happens. Remember what we said is that no matter what your initial concentrations or pressures are going to be, it's going to come to equilibrium until this ratio is equal to that value. So what I'm going to do is I'm going to calculate what's called QP. And QP, all you do is you put in the pressures that are given into the equilibrium expression for KP. So ammonia is 0. So 0 squared divided by nitrogen is 11. I'm not putting units in. And then hydrogen is 7.5 to the third power, right? Over to the third power. Well, that's equal to 0, right? If the numerator is 0 and the denominators are values greater than 0, then you're going to have 0 for Q. And here's what you want to remember. If Q, whether it's QC or QP, is less than K, then what will happen is the reaction, the terminology we use is it will shift to the right. Okay, the reaction will shift to the right. If Q is greater than K, then the reaction will shift to the left. Strangely enough, that's the terminology we use, okay? From a molecular perspective, here's what's happening. In order to be at equilibrium, which we can in a sense think of as a form of stability, that ratio has to be around 3 times 10 to the minus 7. So if the ratio is 0, that's less than 3 times 10 to the minus 7. So here's what will happen. Remember, there's 2 reactions occurring simultaneously, the forward and the reverse, forward, reverse. What will happen is if this is 0 over here, these reactants will form product, but there won't be any product to form reactant. So you'll start forming more product, and you really won't be forming any more reactant because there's just too little product to form reactant. You know what I mean? Remember, the rate is proportional to the concentration of the reactant. So if there's no ammonia, ammonia can't really form nitrogen and hydrogen. The reverse reaction can't really happen. On the other hand, if there is a lot of nitrogen and a lot of hydrogen, then there's plenty of reactants to form ammonia. So the reaction will do this. We'll get a change. And what will happen is this will go down. So I'm going to put a negative, meaning it will decrease. And I'm going to use the symbol X to indicate it's by some amount that we don't know what. Okay. Likewise, the hydrogen will go down also, but it will go down 3 times faster because there's 3 times as much of it in the reaction equation. So every time 1 nitrogen reacts, 3 hydrogens will react. So it'll go down 3 times as fast, right? And so here's what will happen on the product side. this one will go up. And it'll go up twice as fast as nitrogen is going down. So plus 2x. All I'm doing is I'm using the coefficients in front of the x's. So it's not all complicated. I'll just, whatever that coefficient is, that's what goes in front of the x. So is Q less than K? Yes, it is, because Q is 0 because there's no ammonia initially. So the reaction will shift to the right. If it shifts to the right, that's really what I'm showing here mathematically. This means shift to the right. The product is going up. The reactants are going down. That means shifting to the right. Okay. So now at equilibrium, here's what happens. You start off at 11 and you go down by some amount. We still don't know by how much. We're actually going to figure out by how much in a moment. You start off at 7.5 and you go down by some amount, 3 times as much as you did for nitrogen. And you start off at 0 and you go up by 2x. So that's just 2x, right? Okay, all right. So now here's the cool mathematics of this. What I'm going to do is I'm going to say these are equilibrium pressures. So I can substitute all 3 of them back into this expression. All of them can go right on into that expression. So Kp, which is 3 times 10 to the minus 7, is going to be equal to the pressure of ammonia squared at equilibrium. So that's 2x. That's the pressure of ammonia at equilibrium. But you have to square it because you got a square there. And then we're going to divide that by the pressure of nitrogen at equilibrium, which is 11 minus x. And then you're going to divide it by the pressure of hydrogen cubed. So that would be 7.5 minus 3x cubed. And that's going to be equal to 3 times 10 to the minus 7. Okay. Now, here's what we can do. The question in this particular example says, can you predict the equilibrium pressure of ammonia? That's NH3. So, can we find the pressure of ammonia at equilibrium? Well, it really just depends on whether we can solve this equation. We have a number on the right side, but we have all these x's on the left side. But remember, there's this form of mathematics where you have numbers and symbols, right? And you use them to solve problems, and it's called algebra, right? Well, that's exactly what we have here. We have an algebra problem. So if we can solve for x, that will actually tell us the concentrations. And here's why. At equilibrium, 2x, that is the pressure of ammonia at equilibrium. So if you can solve equilibrium, if you can solve for 2x, you can solve this problem. Now here's the challenging difficulty of this. There's some pretty big exponents that make this algebraically a difficult problem to solve. Generally, when you take algebra, you learn how to solve first order and second order equations, maybe third. Fourth, getting kind of tricky. So in this one, we have a fourth, but here's our approximation. This is why this problem is called the small x approximation. If x is really small, then, so if x is small, so if it's not less than, how do you put this in mathematical terms? You say if x is approximately 0, I'm not saying it's 0, I'm just saying it's approximately 0. If it's really small, okay, then 11 minus x is approximately equal to 11. You can try that yourself, right? If x is 0.01, 11 minus 0.01 is approximately 11. So, and the same is true for 7.5. So if x is approximately equal to 0, then 7.5 minus 3x is approximately equal to 7.5. And that is going to solve our algebra problem. Because if 11 minus x is approximately equal to 11, I just can substitute 11 there. If 7.5 minus 3x is just equal to 7.5, I can just put 7.5 cubed there. Okay, and now that's equal to 3 times 10 to the minus 7. Now we can solve for 2x. We just need to have 2x, which is the ammonia concentration equilibrium. Now, how do I know if I can make that assumption? Well, if it really kind of depends on this value. If that value is much less than 1, usually you can make that assumption. There's some details in all of that, but if it's a small value of k, all of these ones in this particular problem set are going to be small values of k. You can make that assumption. Now, I can't say that it's equal to 0, so I'm not going to get rid of the 2x up here, but 11 minus x or 7.5 minus 3x, those are approximately equal to those numbers. Okay, so now I can just say, look, I'll put a little arrow here. 2x squared would be equal to 3 times 10 to the minus 7 times 11 times 7.5 cubed. Okay, so you can do that arithmetic, right? It's 3 times 10 to the minus 7 times 11 times 7.5 raised to the third power. And you get 0.00139. So now, if we want to find 2x, we just take the square root of both sides, right? 2x squared, the square root of that would be 2x. So we take the square root of both sides. Okay, so take the square root of that side, and that's going to give us 0.037. I think they said actually just rounded to one significant figure. So 0.04 would be one significant digit. Okay, so it is pretty small, right? According to that approximation. Turns out that's pretty good. It works out okay. Okay. A lot in that one, right? This is not a simple one. I'm going to show you one more, okay, and then you can start practicing these on your own. We'll look at similar types of problems in the next section. We'll get to 5.4. Okay. This is where the math really kind of gets at you here. Okay. All right. Again, small x approximation. Okay, so what that means is the initial concentration minus x is approximately equal to the initial concentration. That'll be our setup. Okay, see how that's the same equation? I'm going to show you a different one because I want to see if I can find a different equation. Let's try this one. I don't want to do the same equation each time. Okay, so 302 converts to 203. There's our k. See how k is small? You can make that small x approximation if k is small. So here's what we do. We fill the vessel, the container, with 5 atmospheres of oxygen. And we want to answer the question, can you predict the pressure of O3 using only the tools available? And then if you said yes, enter the equilibrium pressure of O3 at the right, okay? So like I said, with all these problems, as far as I can tell, the answer is always yes. If we have the right mathematical tools, okay? So let's 1 times 10 to the minus 5. So this is a interesting equation. It's 302 goes to 203, and then Kp, I'm going to go ahead and write it out. It's equal to the pressure of O3 squared, right, over the pressure of O2 cubed. And this is equal to 1 times 10 to the minus 5. Okay. I have to admit, it's a cool problem. It's not actually one that I had seen before in general chemistry textbooks, but it's kind of cool. It's actually logical. So here's our initial 5 atmospheres. And then again, this is 0. If it doesn't say there's any, it would tell you if there was some, so it must be 0. So we calculate Q. So when you calculate in Q, you just take your numbers and put them into this expression here. So 0 squared divided by the pressure of O2 is 5.0 cubed. Well, that's 0, right? So that means that Q is less than K because it's 0, right? 0 is less than any number that's above 0, right? So that means the reaction is going to go this way. It's going to shift to the right. Make a little 3x5 card. Q is less than K, shift to the right. Q is equal to K, it's at equilibrium and you're done. You don't get many problems like that. They're not going to give you an easy one like that. Q is greater than K, shifts to the left. Okay, now the meaning of that in terms of the arithmetic, in terms of the algebra, is that if Q is less than K, that means you're going to have your minus X on this side and your plus X on this side. Oops, let me get that right. Okay, so if you're doing shift to the right, okay. Let me put the other one. So that was right. So you get minus X goes to plus X. Now, if Q is greater than K, that means shift to the left, and that's where you're going to get plus X on this side and minus X on that side. Okay, that's the information you need. So remember, you have the 3 there. So minus 3X, and then you have the 2 there plus 2X. So at equilibrium, all I do is I take these and I add them. 5.0 minus 3X, you're just combining them. It's kind of like I say, I start off with $20, I give away 10. I have 10 left over. You're just adding them, you know, 20 plus a negative 10 is 10. 0 plus 2X is 2X. Now these are equilibrium, so that means that we can substitute them into this K expression. So KP is equal to, don't forget here, you got that squared. So 2X squared over 5 minus 3X, but it's cubed because you get that cube there. That's what makes this mathematically a challenge, is once you start getting up to cubic values, you know, that's tough. But there's a trick out of this, and that is because K is small, we can use the small x approximation. The small x approximation says that an initial concentration, if it's sufficiently large, minus or plus a small value of X will be approximately equal to that initial concentration or pressure. So 5 minus 3X is just going to be 5 minus, it's just going to be 5. So we're not going to get rid of the X up here, but we're going to get rid of it in the denominator because 5 minus 3 times 0.001 is essentially 5. Okay. And that's going to be equal to 1 times 10 to the minus 5. That's the small x approximation we just made right there. So 5 cubed is, what is that? 5 times 5 is 25. It's 125. So 2x squared is going to be 1 times 10 to the minus 5 times 5.0 cubed. So that's going to be 1.25 times 10 to the minus 3, I think is what it works out to. 1.25 times 10 to the minus 3. I think that's right. And that's going to be 2x. Now, if you take a look at it, 2x is the equilibrium pressure of ozone. That's what the question is. What's the equilibrium pressure of ozone of O3? So the answer is yes, we figured it out. If we take the square root of both sides, because you got to get rid of that squared. So now I'll do it over here. 2x is going to be equal to the square root of 1.25 times 10 to the minus 3. Okay. So 1.25 times 10 to the minus 3. Take the square root and you get 0.158. It says to one significant digit. So I'm going to write 0.158. I guess that's atmospheres, right? Or 0.2. That would be one significant digit right there. Okay, one digit. There you go, guys. That's it. So that is the end of section 15.3. We have 2 problems from 15.4 and 2 problems from 15.5. So we'll wrap those up this week or weekend. They'll come at you pretty soon. And then we'll move on to the next one. Okay. Take care.